Welcome to Part 2 of the Wireless Control Foundation short course.
As Mark indicated, there's a lot about wireless in terms of just the information that's provided, understanding what it's telling you. But one of the key things in terms of using wireless is setting up this communication rate that Mark talked about. As you saw from the graphic there, as you increase the speed with which information is communicated, then your battery life is greatly decreased. And so if you think about that and you think about process control, that is using these measurements in control, then at first it seems like maybe this isn't really possible in terms of doing control. And it's true, it's not possible to do it the way we've been used to doing it. So if you look at the way we've been used to doing process control, so if you look at the way traditionally we've looked at control, the recommendation is that you need at least 4 control executions over your process response time, where process response time is defined as the time from you making a change to getting to 63% of the change. So it's your dead time plus your time constant, it's the process response. Now if you're Boeing and you're designing an airplane, they probably tell you you need to at least execute 10 times over there. But at least for the process industry, 4 seems to be a pretty good value. You can always go faster, but to minimize any delay that's introduced into our control, then the actual I/O access is much, much faster than the actual control execution. For example, in delta V, the hard transmitter that you have is updating that 4 to 20 milliamp signal at least every 50 milliseconds. So you get fresh updates every 50 milliseconds on your 4 to 20. That comes into the I/O cards. So let's say you're using the traditional I/O card, then our rail bus is scanned and put into memory every 50 milliseconds. So if you think about when you execute control, then the information is on average no more than about 50 milliseconds old when you use it in control. So the delay introduced in control is very small. And as soon as you execute, then going out in the other direction, again, very fast response. So you minimize delay, pure dead time in your control. And as we all know, dead times are enemy in terms of doing control. So if you now think about, well, I would like to execute in that way with wireless, your battery will last maybe a week, if you could actually communicate that fast. So really not possible to do that. In most cases, people are looking at a 5 to 7 year battery life. That means realistically your update on terms of I/O is about every 8 seconds. And with an 8-second update, then you're in this region of a 5 to 7 year battery life. With some devices, you may even be talking about a 16-second update to achieve that length of battery life. Now then, if you have a slower application, like maybe a temperature loop, maybe a composition, where the process response time is slower than 30 seconds, you can use that 8-second update. You're getting at least 4 updates then over your process response time. And you can use regular old PID, and it looks pretty good in terms of the response. So here we're looking at a set point change wirelessly with an update every 4 times over the process response time. Here we're introducing an unmeasured disturbance, so we're being driven away from set point we have to recover. And again, if you compare that to your wired installation, it looks very much the same. So you can get very, very good control as long as you can get information and do control 4 times over your process response time. Now then, if you violate that rule, then things aren't so good if you're using PID. So for example, if you're updating two times slower than your process response time, So let's say you have that liquid flow loop where your response time is maybe 3 seconds. Twice that would be a communication update of 6 seconds. In that particular case, this is the kind of thing you would actually see. And most people wouldn't want that in their plant in terms of process control. Now then, this is using the tuning that we would use with a wired installation. And you say, well, Terry, I could take some of this out by slowing down my reset. And for sure you could. But if you did that, your response to disturbances would really be pretty bad. So realistically, once you get faster than about 30 seconds, and if you're using an 8-second update, you need to do something different than PID. So I tell people, and what we had in the book was this little chart that says, up until introduction of wireless, we've been very successful at mimicking analog control in our DCS. We've designed the I/O, we've designed the control, everything where we can essentially do what we used to do with an analog controller. But now when you start talking about wireless and you look at the reality of how fast you can update and have a decent battery life, you really need to work with a different way of doing control, at least on your faster applications, those that respond faster than 30 seconds. And fortunately, that's very, very possible to do. What it takes is to restructure your PID into what we call the PID plus. With the PID plus, you don't modify the way the proportional action is taken. But what you do modify is the way the reset component is calculated. And also, I don't show it on here, but if you have derivative, the way the derivative is calculated. And so with PID plus, then we calculate those in a very different manner to accommodate these varying and slow updates that we'll get from a wireless transmitter. So this shows then, if you're doing derivative, then we look at the time between new communications, look at the change between new communications, and make our derivative based upon that. Your normal PID looks at the time between control executions. Now, with PID plus, we sort of take the cart and turn it totally around. That is, where with wired systems, your I/O is coming in extremely fast, and maybe your control isn't so fast. With wireless, what you're talking about doing is having the control execute extremely fast, even though you're using an update of, say, 8 seconds. By doing that, you minimize the time between a new measurement coming in and actually being acted upon and controlled. So we're again trying to minimize that dead time we introduce into the control system. Okay, so, but that means that this needs to be done differently. So with PID plus, if you compared it to a wired system, which we're doing here, and here we're using that exception reporting Mark was talking about, where if the measurement changes by more than 1% from its last communication, or if it's been a certain default time since the last communication, it gets communicated. Otherwise, it doesn't get communicated. So you get non-periodic updates with this. Here you notice on a set point change, we're comparing this to a wired installation with PID. You notice with PID plus and wireless, it's very, very much the same response that you'd expect with a wired installation for a set point change. That's the valve for the wireless versus wired. For introduction of a disturbance, we're driven away from set point. You notice that the wireless doesn't quite do as well, and that's because we really can't take action until we get a new communication. That is, we're unaware of the disturbance. So in this case, it could have been 10 seconds before we really knew what was going on. So that means that we don't catch the disturbance quite as fast. But you notice, quite interestingly, when it does take action with PID+, the valve position is the same as though you had had a wired installation. Okay. So overall, the response is fairly good. Now, you know, most people that have installed wireless just for monitoring have seen that it's pretty reliable stuff. But there's always this question of, well, what happens if I lose communication? Something were to happen. Then what happens with PID Plus versus, say, if I'd had a wired installation and for some reason my measurement froze on me? Well, in this particular case, if you look on a set point change, we're changing set point, and at that point, we simulate a loss of communication. You notice the PID Plus handles it quite well. If you had had PID on that same thing, it does this kind of thing, right? That's your reset action acting upon an error where the error doesn't respond to your valve anymore because you've lost communication there. And you don't get such a great response. This eventually would drive you to 0 or 100% if it remained long enough. So with PID Plus, it's really recommended if you have a faster process that you use that in control. And it's as simple as going to your FRS PID option and selecting PID Plus, and now you have that capability. So that's really all that's required to have that. Yes?
Would the PID Plus be used with any communication that has a tendency to drop? Or thinking modulus or something else where...
Sure. Yeah, it's a great question. It can really be used with, like you say, any communication system. What we're doing in here is we're looking at the measurement. Did it change in the 6th decimal place to say you have a new value? And so really if you have some kind of other wireless or wired communication that's really not updated very frequently, then would really recommend you use this. Also, if you have sampled analyzers, you know, if you have a gas chromatograph that's updating every 5 minutes, say, then in the older times, you know, the way we addressed that is we had a PID and you had a special algorithm that turned off the reset after a period of time, and you had to muck around with the tuning and everything to try to make it work right. Here, you actually just put the tuning in the PID of the process response. So you look at the process dead time, time constant, set your reset equal to that, and then adjust the gain to get the response you want. And with your gas chromatograph updating every 5 seconds, you'll see every 5 minutes, you'll see it would make a change every 5 minutes due to the new value coming in. But if an operator came in and changed the set point, it would immediately respond to that. So it really is a wonderful technique for any kind of input, measurement input, where there is, it's help for a period of time. Now, having said that, when you use wireless or any other input that is not being updated constantly, it's critical that you don't put filtering in the path of control. And you say, well, why is that? Well, in the wireless heart, part of the standard is that there's a timestamp that always gets communicated with your new measurement value. But in Delta V, unfortunately, we don't use that in the module right now. And so the only way we can determine you have a new measurement here is to look, did the measurement value change in like the 6th decimal place? And usually almost on any measurement at the 6th decimal place, between one measurement to the next, it's changing. So that's the way we detect you've got a new value. But if you have applied filtering here, when you get a new measurement, it changes, but then it continues to change due to the filtering right here, which would fool the PID into thinking, I've got a new measurement, error execution, which really would defeat PID plus. So if you need filtering in your control path, then the recommendation is use the dampening at your transmitter. Don't put filtering in the control path in your module. Okay, and like I mentioned earlier, you want to set your execution rate quite fast in terms of your module, much faster than your communication. This allows us then to minimize any delay between the measurement coming in and taking action on it. And dead time is our enemy in terms of control, This minimizes that dead time by doing that. So when we originally developed this, we did a lot of simulation, just to check it out and verify it worked the way we thought it would. But we wanted to try it on some real processes. So one of the first processes we tried it on was at Broadley James. We were doing other work with Broadley James, and Scott Broadley was nice enough to say, yeah, I'll be glad to try this out. So this is a disposable bioreactor. The inner lining here is disposable. They throw it away after each batch. It's something that's happening in the pharmaceutical industry to avoid having to tie up equipment cleaning and that kind of thing. So in that particular case, you notice it's mounted on wheels, so they cart it around maybe the factory. And so it made some sense to say, let's put some wireless measurements on here. And so we did that, and this was around 2009 time frame. So these were some of the very first devices out there, very first gateways out there. In that particular case, then we took the pH as well as the temperature, both of them really critical parameters of the batch. And they actually ran some batches using mammalian cells, cultures, just as they would in a regular plant. And here's the response using wireless for temperature control. So you look at that, looks pretty good for that. And this is on pH response. And you look at the units over here, really very, very precise pH control. Now then, this is incredible response, but if you look at the time frame here, it's really a pretty slow process, right? And so it wouldn't have really required PID plus using that wireless measurement because it's such a slow process here. Okay. So we wanted to, but it did prove out using wireless that is a viable thing to be doing. But then we went to UT, as Mark mentioned. We do a lot of work with them. And on this absorber stripper columns that they have, we're working with the Department of Energy to sort of prove out this ability to take CO2 out of flue gases and pump it back down into the ground, So this is something that the government was funding. So anyway, on this stripper absorber, we instrumented it with wireless transmitters on some critical things, the column pressure and the actual steam flow for the bottoms. And so this shows the operator interface, and we had it set up where you could switch between wireless and wired. So we could then do a comparison, do a run with wired, do a run with wireless. And this is showing then the wired control, and this is on, I think this is on the column pressure, which is, those of you who have run columns know, critical kind of thing to be running with. And this is where we had a campaign where we used the wireless measurement. But if you look at that, it's difficult to really tell you're with wireless. And yet the pressure control is quite responsive, quite fast. And the same thing on the steam flow. I'm not showing it here, but it was a comparable control on steam flow. So if you compare interval of absolute error between these, you do notice that with wireless it's not quite as good as with wired. But the important thing to notice is that the number of communications using wireless is significantly fewer than the number of new measurements you would have used with wired, right? So you can do comparable control with fewer new values is the main point here. So in the book, there's a whole chapter on using wireless measurements and control, going through the principles of the PID, much more than we can talk about here today. But if you're really interested in knowing the details of that, please read that chapter and you'll learn more about it. We also had a chapter that was sort of looking forward to total wireless control, where you have now wireless valve as well as a wireless transmitter. And a lot of this is actually being driven by the oil and gas industry in terms of upstream oil and gas production. The installation cost of some of these well sites is really driven by the cost of wiring in some of these remote locations. And so if you can go totally wireless, could really be a big breakthrough in savings. So we're okay in terms of the wireless measurement, but the wireless valve is something that we're working with Fisher Controls and Rosemont in terms of coming up with a wireless throttling valve that you can apply. And there are adapters today where you can actually have a throttling valve that wirelessly you can communicate with, but there are some technical barriers right now in terms of doing fast processes with that. So in theory, if you're talking to an actuator out here that's wireless, if you could get back the position, then rather than taking the output of the PID, going back in this positive feedback network that creates the reset, you could just bring in the actuator position and use it here. So it should be just that simple to be able to compensate for any delays in the requested valve position getting to the actuator. But the reality of it is that it can take quite a while to get down to the actuator, but it also can take quite a while for that response to come back, because in wireless HART today, downstream communications are not scheduled. So you have to find a free time in the schedule before that value goes down. So you'll see varying times and quite long times sometimes in terms of the actual value going down to your valve if you're using a wireless valve. Okay, so we've been working with Fisher Controls and Rosemont then in terms of the gateway, looking at how do we address that. And one of the things that we knew was that the actuator, if you're going to make it totally wireless, most of the power is used when the valve is moving. That is, if it's not moving, there's actually some technology that Rosemont or Fisher Controls is working on where it requires no power as long as you're not moving the valve, no energy required. So, but that means that, if you look at your valve in your plant, normally your valve is sitting there constantly moving almost. So you say, well, that could easily burn up a battery. How do I address that? So what we've done is sort of investigate this non-periodic control communication, which says that only if the value is changed by more than a dead band, or it's been more than a certain period of time since I last changed it, will I actually change the valve position. Okay, so we periodically evaluate, has it exceeded the dead band? If it has, it's communicated, or if it has been a certain period of time, we'll go ahead and communicate it anyway. So this is something that, on the surface you say, can I really do that with my valve? What does that do to me from a control standpoint? And it turns out that it's easily accommodated. So we wanted to test out the wireless valve in a real live application. We've done a lot of testing and simulation, but as we all know, in a simulation world, sometimes you can get the wrong idea about something because you haven't maybe been able to simulate all the different features that you'll find in the field. So Fisher Controls has a really nice flow lab, one of the world's largest there. And they gave us one of their corner applications there where we could evaluate this. And so on the Coriolis flow meter, we put a thumb on there to get the flow measurement wirelessly. We could also see it wired, so that allowed us to sort of go between wired and wireless. And then we had, in the flow line, we had what we called a load valve, where we could change the valve, and it increased the restriction downstream of the valve we were actually using in the test. So we can introduce disturbances in our flow loop by changing the load valve. So the actual valve we were testing, the prototype here, is not really shown too well. on the edge there, but that's the valve we were adjusting. So just to give you an idea of this process for a wired installation, we used the delta V tune to tune the loop because we didn't want to be accused of any kind of special tuning or any kind of special knowledge, right? So we used the delta V tune to tune it, and using wired measurements and wired valve. And you notice there's some interesting things happening in here. You know, it's not a nice smooth curve you might think. And there's some things that are occurring dynamically where you have these tanks that are being used in this flow loop that are somewhat interacting there. So, but this is what it is with a wired installation. So, and this is where we've introduced a disturbance. And that's the kind of response you get with wired transmitter, wired valve, properly tuned. So we then ran a test where we had a wired transmitter, but the valve is now wireless. And in this, we were using this new command called time to apply. So when we change a valve position or send a request, we say change valve position a certain period of time out in the future. So by doing that, we then know the valve is going to change at this period of time, irregardless of how long it takes to get to the valve. Like it may take 1 second, it may take 3 seconds. But if you say the time to apply is 8 seconds, well, you know 8 seconds from me issuing the command, the valve really is going to change. So even though we can't measure the stem position, we know the stem position, okay, by using this time to apply. And so using the time to apply, and actually in this case I've set it 8 seconds, because if you look at this bell curve of the time delay and the valve actually acting on the command, at the far extreme was like 8 seconds. So if you notice here with the time to apply of 8 seconds, the response looks remarkably like what you had with a wired valve. But the main difference is that there's this 8-second pause right there, right, before you actually see change. Okay. But that's the main difference. You don't see any hunting, anything going on here. And the amazing thing is the tuning of this is the same tuning we used with the wired valve. No changes in tuning, right? And this is for unmeasured disturbance. Again, if you compared it to the wired, very, very similar response. So that gives you a little bit of future thinking about things that you'll see coming. We're working with the Heart Foundation in terms of getting this time to apply command as a standard Heart command. And we're working towards getting that command supported in the gateway and in Delta V in version 14. So if things hold on schedule, we'll do it at that time. But you never know about schedules, right? But we'll do our best to see if we can do that.